Good evening, guys. How things are going? Hello.
Good, sir. Good evening, sir.
Good evening. So, how things are going?
Fine, sir.
So, how many of you are able to run that case study?
I did.
So, okay. So, you have done it. So, how much accuracy you are getting it?
Sir, on the last epoch, I got 81.55.
Okay. So, I think all of them have done, or still people are there who have not done it or not downloaded data. So, what is scenario? Actually, I told last class that people who have not downloaded data, they can download it and then we'll run case study quickly. So what is scenario actually? I want to understand. And it seems very few people have joined class. Where is Rajnikant? So Meena, are you getting? So you have messaged Meena that you are getting some low score.
Yes, sir.
So are you able to improve the accuracy?
No, sir. I was trying it. I didn't get it, sir.
Okay. What happened to Harshit Agarwal? Have you completed case study?
Sir, I did not attend the last class due to some reasons. I'll
That's
do
what
it
I
today.
was asking. So have you downloaded data?
Yes, sir, I have downloaded the data. I'll do it today.
So
I'll
you know,
message you after.
so you know exactly how to do it.
Maybe I'll take the help of my colleagues or I'll see the recorded lecture. Then I'll get back to you.
Okay. And what about Pavan Kumar? Pavan Kumar 98. What happened? He had just joined it and then left. Okay. Abhishek,
Yes, sir. I did it in
what is
last
your
class.
scenario?
I did it in last class, sir.
Yeah. So how was your accuracy?
81.42.
Very good. So you people, I think, managed to get good accuracy. Now I think you know how to get good accuracy, correct?
Yes, sir.
So it is on validation set or test set, training set. So do one thing actually. Okay. Uh, okay. Let me check others also. Kunal Kumar. Kunal ji. What is your status? What happened to Kunal? And what about this Raja Vinny 68? What happened? These people just join class and then leave. What's happening? Veer Pratap. Satendra already you have told me, na? And Veer Pratap.
Yes, sir.
What is your status? What is your status about the case study?
Sir, actually, I have not downloaded that file, sir. Yeah, due to electricity problem.
Yes, Khandelwal.
Yes, sir.
What is your status, boss?
Sir, actually, I have not attended last class, so I will watch the recorded lecture today. And
So if you are planning to do it today, why not you have done it before 2 days? Saturday, Sunday, you don't have the holiday?
Sunday only, sir.
So you people supposed to work now. If you don't work, how do you learn thing? Otherwise, this course also be like your first machine learning, where you have not understood anything. So you have to do it, no? Who will do it?
Yes, sir.
You are not going to do. You have to learn, or just you are just for sake you are just attending classes and then course.
No, sir, I will do it today.
You do it and message me. Okay.
Okay, sir.
Okay. So today we are going to have theory class, and then some part of that case study is pending. We'll do it today. But first we'll see theory, some theory. Okay. Can you see my screen?
Yes, sir.
Okay. So who is going to tell me convolution operation? How many of you remember this convolution operation? All of you? Okay. Who is going to summarize how CNN works? I will pick people today because what I feel is just you people are enjoying. So, Meena, can you tell me exactly how CNN works? And it is going to, I am going to note name whether they are answering or not. I will just mark it today. So, Meena, can you explain me how the CNN works? Meena, can you listen me? Yes, Khandelwal, can you explain?
Yes, sir.
Yeah.
So, in convolution, we will find solutions for
Harshit Agrawal, can you explain?
Hello. Yes, sir.
Yeah, Harshit.
Uh, Actually, in convolutional neural network, as far as I have learned, there is a feature detector representing in a form of a matrix, and we do the convolutional operation and detect the images in the form of that are in the form of pixels with different layers and different feature detector that we also called as a filter, and in the form of that we try to detect the images which is our main goal.
That is okay. Can you tell me what are the different operation we do it in CNN? So
Sorry, sir.
let's say I give you image, and can you explain me from image to training a network how the step evolved?
No, sir. Sorry.
Very good. Sunil Gupta.
Sir, we convert the image into matrix. Hello, can you hear me,
Yeah,
sir?
yeah. Yes,
Sir, we
yes.
convert the image into matrix where in an image where color is there, we put 1. In a wide space, we put 0. We'll create a matrix, then convolution process, convolution layer, then max pooling, then flattering. Finally, the input layer is
So what is the objective of max pooling?
what?
Why do we do max pooling?
Just 1 minute, sir. For flattering.
So we do max pooling for flattering. So why not?
Sir, for
You
pooled
people,
features map.
so
Sorry.
anyway, you people have recording. Why not you just have a look when you are free?
Okay, sir.
Okay, so one operation in. So we'll come to today lecture actually. I'm very upset. You people have to revise it actually. If you don't do it, you will not learn it. And I am not going to lose anything. You are only loser. See, each and every case study I used to discuss after class actually, so that whatever we have learned in class, try to implement it. But if you are not understanding theory, you have to tell me you have not understand it. I'll just try to make it one more time. If you are not understanding case study, you have to tell me I have not understood. And we will do it again. So can voluntarily anyone can explain how the CNN works? No one want to take a try.
Sir, first step is data processing, where we break all whole image into the pixels, which is in matrix form. After that, we do the convolution, and after convolution, we do the flattening.
No, after this, we have activation stage where we do
Activation, yes, activation function.
then-
We connect
and then after that also there's something,
output layer.
and then we do max pooling,
Activation.
and then flattening comes. So we will start with convolution. Actually, I have to teach you some another concept in convolution operation. So we'll just look it quickly, and then I will also teach what are the different architecture available for CNN and what are the famous architecture of CNN. Okay. So we have seen how this convolution works, correct? So we have the input image which is made up of pixels, and then we have feature detector which we also call feature. We convolve together and then we get a feature maps. So we know exactly how this works. So it is the element wise matrix multiplication, correct? And then we take sum of all this and put it into respective feature image, correct? So this is the way we do it. So in convolution, another concept is called stride. So basically in this, we take first 3 row and first 3 column and do convolution step. And what, let me take pointer. Just a minute, boss. So first we will understand, is this a pointer? Which one is pointer? Yeah. So can you see my pointer?
Yes, sir.
So in convolution operation, we have an input image which is made up of pixel. Another, we have to convolve it with a feature detector, or we call as a feature. Another name people call this as a kernel also. Okay, and then we get a feature map. So how does it work? So this is, so our filter is 3x3 filter. So what we will do is we will go and get the 3x3 matrix, first 3x3 matrix in input image, and then we do element wise multiplication and then sum it out and write it here. Then what we will do, we will go and take another, we'll just leave first 3 rows, and then we'll go and take this from column 2 to column 4 we'll take, and row from row 1 to 3 we'll take, and then we'll do the convolution operation. We'll get the next one. So at a time we are leaving 1 pixel actually. Similarly, there is something called stride. So stride is number of pixels shift over the input matrix. When the stride is 1, then we move 1 pixel at a time, and when stride is 2, then we move 2 pixel at a time. Okay, so there we were leaving 1 pixel at a time, but sometimes when you have to reduce dimension further, we have to take stride equal to more than 1. So let's say we are taking stride equal to 2. So how does it work? So first, again we have same input matrix, correct, and same filter matrix. So how it is going to work is, we will first again start with taking the first 3x3 matrix from the input image, convolved with this filter image, and write it here, correct. And second time we have to leave 2 pixels. So first and second we will leave, okay, and then we will take this 3x3, okay, means third, fourth, fifth column we will take, and then we will take this 3x3. Are you following me or not? Initially we were leaving 1 pixel, now we are leaving 2 pixel at a time. Okay, so we'll take this 3x3 and then we'll write it here. Then again we will leave another 2, and last 3x3 will take and write it here. Similarly, when you go down actually, then you have to leave first 2 row, and then we have to go and take this 3x3, correct. First 2 row we have to leave, and then we have to take this 3x3, correct. And then again we have to leave this 2 row, and then again we have to take 3x3. What I want you, so have you understood this?
Yes, sir.
Yes, sir.
How this
Sir, one
operation we are
question.
going to, yeah.
What if this metric is of 9 by 9?
Okay, so again we have to do same operation actually. Okay, you have to do same operation. So what happen is, sometimes some pixel may not be used actually, but if you want to use all this pixel, then there is a concept called padding. So we will come to next slide. Okay, I'm also going to teach you actually padding. Okay, so if your matrix input matrix dimension is not matching with your feature detector dimension, or it may be some pixel is left out, so there is a way to handle it, and that's we are going to see it next. But now what I want you people to just fill these numbers. Okay, I have just filled 4, and I told you exactly what to do. Okay, you have to fill this number, and then also I will tell you exactly what is the formula to get this dimension actually. Now we have like 7x7 matrix convolved with 3x3, and we are getting a feature map. So what will be the dimension of feature map based on the so you have seen it, correct. So when we have stride equal to 1, we have slightly bigger matrix. When we have used stride equal to 2, we have slightly smaller feature map, correct. Have you observed this? Because our input matrix image and feature detector I didn't change, and we are doing same convolution operation. So something is changing actually, and how to get the dimension of feature map. All the things we'll see today. Okay. So what I want you people to just fill these numbers. So fill this matrix. I'm giving you 5-minute times. We'll just meet after 5 minutes. Okay.
This second row will be 101.
So you're saying second row will be 1, 0, 1. So this is going to be this matrix 0, 0, 0, 0. No, it's supposed to be 0, no? No?
101.
1, 0, 1. Okay, you are saying second term is anyway 0, no? Okay. And what about third one?
Calculating, sir. Third will be, sir, 0, 1, 1.
So what? So all of you have done this. Any other observation? Any other observation?
No, sir, same.
Okay. So come to this padding actually, and then what question you had when our dimension is not matching, what we'll do? So that we handle using padding actually. Okay, so what it says that sometimes filter do not fit perfectly, and therefore to do convolution operation we need to do following actually. So one is zero padding. So you have to, zero padding means you have to fill a layer of zero so that it can fit. Correct. If you find that is a dimension mismatch, you just add zero Okay. So either you padding is equal to 1 means one layer of 0 you are adding. Padding is equal to 2 means two layer of 0 you are adding. Okay. Other option is if you don't want to add 0, so another option is you just drop the dimension where your filter matrix does not fit it actually, and that is called a valid padding. So you have to drop the part of the image where the filter did not fit and keep only the valid part of image. Understood?
Yes, sir.
So I
Yes, sir.
okay. Let's say I am saying you have a pixel matrix of dimension n cross n. Just just try to understand that. So what does it mean actually? What n cross n? What does it represent?
And column and row.
So basically, what it represents is n is height of the image, and another n represents this width of image. Correct? And let's say you have not done padding. One padding is equal to 1 means we are just adding 0 outside of this matrix. Now, what is dimension of our matrix? N cross n. Correct? After padding, what will be my dimension?
N plus 2, N plus 2.
So All people agree with it. Our new metric dimension will be n plus 2 cross n plus 2. Correct? Because both sides we have added one layer of 0. So we have added 2 rows and 2 columns. Therefore, our dimension will be n plus 2 cross n plus 2. Correct? So these two
Yes, sir.
concepts. So these two concepts actually I thought to discuss it because these are practical scenario actually. So I thought convolution anyway we have discussed it where stride is equal to 1, but we have not discussed when we'll have not stride is equal to 1 because I have seen lots of this architecture where they use different number of stride actually, and then they use different number of padding actually. So I thought to discuss this so that when you read some paper or some literature, you should have good understanding. Okay. So what we are going to see now is different architecture of popular CNN model. And what does this architecture means? So what is architecture of deep learning model? How do you tell me if I say that we already have completed this neural network? So if I ask, can you tell me architecture about your developed neural network model? How do you explain it?
Sir, neuron activation function consists.
So basically, you will tell me how many hidden layer you have, and every hidden layer, how many neurons you have it in hidden layer, and what activation function you have used it in hidden layer. Correct? Or someone give me this information, I will use my data. Similar type of architecture I will also use. Correct? Correct or not? So there are several popular architecture of CNN. Okay, so you can also try this architecture on your image processing task. So let's say, and there is something called transfer learning. How many of you heard about it? Transfer learning. So anyway, we will come later on that. But there are lots of popular architecture of CNN. So you can also try it out in your model. Okay. And then this architecture, you can also use it, by the way. Okay. So if you want to do some image processing task, you can use this architecture to do it. So first architecture was developed in 1998, and I think we have talked about it. It's LeNet actually when we were starting this our introductory the CNN. Correct, and we have talked about LeNet. Do you remember?
Yes, sir. Yes, sir.
Okay. So 1998, they have developed this LeNet, and this was a very successful model. And they have also shown that LeNet can be used in reading postal code, and then also what you call checkbook numbers actually. So this was the first successful model and they are also able to show application of this. So we'll see exactly how this linear architecture is, and then in 2000 another people had published this network called AlexNet. So if someone tell that actually LeNet 5 AlexNet, so you should remember exactly which architecture they are talking. Okay, so these are very famous architecture of CNN. Okay, so after AlexNet 2003, they have published VGG 16. So basically, some group of people work together and then come up with this VGG 16. So if you see all these three, LeNet 5, AlexNet or VGG 16, these are all more or less similar in nature actually. Only thing is they have used different numbers of convolution layer, different numbers of what you call the depth of network are different, and then it may be activation functions were different, but they were all in similar nature. Okay, and after 2003 there's some more development happened, but ground break network what I can see is comes name of ResNet actually. So this is entirely different, not I will say not entirely different, but yes, this is most successful till now. This is the most successful network I can see, and concept is also different compared to all these three: LeNet, VGG net, and AlexNet actually. Okay, so we'll come to all this network one by one. So today what we are going to see this LeNet, AlexNet, and VGG 16. Okay. So by the way, ResNet is developed by Google. So come to this LeNet architecture. We will try to understand, because already we have learned all this concept. You have to know just remember all those concepts. Try to connect with this. Nothing more. So if you start understanding this type of figures and network, you can understand exactly how they represent architecture. You can also represent your problem, whatever you solve with this fashion, so that people understand exactly how your architecture look like.
Sir,
Okay.
these are already built complex neural networks, na?
Yes, these are already built.
And the method to use these neural networks is called transfer learning.
Yes.
Okay, okay.
Okay. So basically what you have to do is you have to just pull this. So architecture, what you are doing when you call this architecture and then apply transfer learning, so you don't have to do much actually. So already you have the base model, base architecture. You have to train your parameter. That's all you have to do, and that also not all parameter. It may be only the final layer you have to train. Okay, so that is the beauty of transfer learning, because so many this model actually they have used lots of images to train all these parameters. So if you, let's say you are just doing some classification model, you can use this LeNet, or let's say not ResNet, what you call AlexNet. This model, just you call that, use what you call transfer learning, and then train your model. That's all you have to do. You don't have to do the which layer will have which activation function, then what will be the filter length, all the thing you don't have to think actually much. Okay. So LeNet were developed in 1998 and they found application it in handwritten digit actually. So this was also a classification problem. If you understand this statement, so this is the classification problem. So it has 2 convolution layer and 3 hidden layer. So we'll try to understand this from this figure. So let's say you have a image of 7. So first, let's say it has a dimension of 32 cross 32. So what is the width? What is the height and width of this image?
32 by 32.
Okay. So I request all of you to just take out pen and paper. Okay. We'll do some sort of calculation also. Just try to understand this architecture. So image is 32 cross 32 and now it convolved with 5 cross 5 5 cross 5 filter dimension is 5 cross 5. So what will be your new matrix dimension or feature map dimension? Can you tell me? So by
28.
So 28 cross 10, 28 cross 28 will be your dimension of feature map. So S is equal to 1 is nothing but your, what is that? Stride. So stride is equal to 1. Means at a time they leave 1 pixel and then do convolution operation. Okay. And what is this 6?
Number of layers.
What is this 6? F is number of filters, correct? Do you remember this figure or not? This figure. They don't do only with one filter, they do with multiple channel or multiple filter. Remember? So this type of filter they have used 6. That's why this is 6 is coming here. And then they are using average pooling. We have learned about max pooling and another concept is average pooling. So in max pooling we do multiplication and then take the max out of it, correct? But here they are using average pooling. Once they have this, again they are doing convolution, next convolution and then average pooling. After this, they have feature map. So this is feature map. This feature map, they flatten it and then pass to the fully connected network. So how much parameter it will have? $400 parameter, na? 16 into 25. How much? 16 into 25. So flattening vector, or you can say that, yeah, vector have how many parameters? How many feature actually? 400.
450.
25 into 16, how much? 450?
Yes, sir.
400.
400.
400, correct. 400, and then it connect with a hidden layer which having 120 neuron, and then they connect with another hidden layer which had 84 neuron, and then they connect with the output layer which having 10 neuron actually, because this is a hand digit numbers from 0 to 9, correct. So you have seen that. So this is the one convolution layer, this is another convolution layer, this is first hidden layer, second, and this is third. So that's why they call this two convolution layer and 3 hidden layers. So
Sir, which one is the first hidden layer?
so what if this one connected with 120 actually? Can you see my pointer?
Yes, sir.
So this is first hidden layer, have 120 neuron. This is second hidden layer, and output layer also they call it a layer actually. Okay, so basically this is output layer, they call it a layer. So this is first, this is second, and this is third. So total numbers of hidden layer and convolution layers including some equal to 5. Okay, so there is a formula actually. If someone give you information of your pixel matrix, then filter size, also the stride information, so you can also go and calculate what will be my size of the convolution matrix. Can you go and check whether it is matching or not? So use this formula, use this number and see is it matching or not. Use this formula. If you have any doubt, you let me know. So next time if you read literature, it will be easy for you to understand all this thing. Okay. Can you use this formula and see is it matching or not?
How much value should we take about for stride? 2 or 1?
Which one?
Stride.
Stride equal to 1. S equal to 1, it is written means you have to take 1. So they also tell exactly stride, how many strides they have. 1 means you have to take 1 here. So padding, they are not using any padding here. The padding you just consider it to 0.
Matching, sir.
Is it matching for you or matching for others also? Is it matching for others also? Can you move? Matching for all, correct? Come to another network. So is it called AlexNet? So developed by Alex. I think this guy is from Russia. Krijiskvi. So all this dangerous name is from there only. Okay. And Geoffrey Hilton. So Geoffrey Hilton is big name actually in image processing, deep learning. And so this network, very famous network because it has own actually ImageNet challenge. And architecture wise, it's similar to LeNet 5. It have much larger and deeper network. So AlexNet have now 8 layers, out of it 5 convolution layer and 3 fully connected layer. Okay. So if you ask exactly what is new in this, so these are first architecture actually. They have implemented rectified linear unit as a activation function, and also they have introduced concept called dropout, and this helps to reduce overfitting. So this is how this architecture look like. AlexNet architecture look like in similar form. So in this, input size is 224 cross 224 cross 3. And what this 3 means? What this 3 means?
Color pick, RGB.
Correct. So this is color pick. This is black and white picks. So they have used black and white images. I think 1998, I don't know, but this guy has used color images. Okay. They have done this convolution operation with the filter having image filter size 11 cross 11. So this is not complete architecture actually, but glance of, you can see glance of architecture. I will also show you complete architecture. How does it look? So this is simplified version of complete architecture, you can think. So R means activation function is after convolution layer, when they have feature map, they have used, after that they have used this activation function ReLU. Then they have done max pooling, then again another layer of convolution, max pooling. And interesting part is here actually. And what is interesting is here, consecutively they have used three convolution operation. Usually what they do is they do convolution operation and they do max pooling actually. But here they have just changed things. They have done consecutively three convolution operation and then they have done max pooling, and then they have three the fully connected layer with different numbers of neurons. Okay, so you can also see there are slightly different in their architecture compared to what this LeNet have. And this is the full architecture of convolution, this AlexNet. So they have image, then they have convolution operation, and then they in this layer they have used 96 filter and stride equal to 4. Then they have max pooling, stride is equal to 2, padding, then stride padding, all this. So the way I have told you and explained you first network, you just try to connect all this and see are you able to connect it or not. So are you able to understand this? Easy or tough?
Yes, sir. No issue.
Easy, na?
Yes, sir.
Once you understood all this concept, next time when you look network, CNN network, na, you will see that all the thing you know already. So nothing is new for you. And another,
After,
yes.
can you go for last slide?
Which slide? This one?
Previous slide.
AlexNet or
Yes. No, next. Yes. No, sir. What you saw now in between the full detailed view of this AlexNet.
Okay, this one? Yeah.
Yes, sir. This one. So after 3x3 max pool strike 2, there are 3 steps. There is nothing changing. What is the operation?
Which one? So this one you are
Add
talking.
one below this, sir.
This one. So this
Below
one you are
this.
3x3
Yes.
convolution. So basically they have done 3 times of convolution operation actually. So basically after convolution operation we used to get a feature map, and then we used to transfer using ReLU and then do max pooling, correct? So that is the usual architecture, CNN architecture. But they have slightly changed it. What they have what they are doing it here, after convolution operation, they get a feature map. Again, this feature map they again convolve with a filter actually. So feature map again convolve, instead of going for a ReLU in a transformation or activation, they again convolve with a feature map, and then again it convolve. Means 3 times they just did convolution operation. Okay.
But size is not changing, does it?
Size is not changing. I have to check actually. I have not checked it whether size is changing or not, but I have to check. This is detailed architecture. If you go and check here, you will find it whether size will change or not. Okay. So you have to do some pen paper work. So I have told you this formula also. Now we have magical formula also. We'll see whether size changes or not. Okay. So we'll come to BGG 16. So this is developed in Visual Geometric Group. So this was developed by this group actually, Visual Geometric Group. So this have 13 convolution and 3 fully network layer carrying with the ReLU tradition from. So activation is ReLU here. So here you can see the network stack more layer. Basically they have just created a deeper layer here, but filter size they have reduced it. And since the more this architecture is more deeper than this, it consists of it contain actually 138 million parameters. Okay, so last two contains around 60 million parameters, and this contains 138 million parameters actually. So if you can ask what is novelty actually, that just it is deeper model. Okay. So this is just a deeper version of LXNet and LeNet. So what you have observed here, from 1998 to I think this developed in 2008 or LeNet, no? BGG 2003 actually. So how many years actually? 2 years here, 5 years. So what you have seen it in 5 year of time frame, how that model evolved. So basically they just try to add more and more deeper layer, convolution layer, and see exactly how they are able to improve the accuracy, correct? So same back propagation approach they are using it to train and get the estimate of the weight and bias of the weight and bias of the network, correct? So let's say, what do you think actually when you keep adding more and more layer, do you think accuracy will increase more and more? What do you think? What is your observation? See, now we have seen it actually. These two networks have performed better than what LeNet was doing, and just what they were doing is just adding more number of layers, either in terms of convolution or it may be in terms of deeper network, correct? So what do you people think? If you add more and more number of layer, do you think we can improve the model performance? Just think, 5 year people had done same thing. They just added more layer and improved, and they won competition also. So what do you people think?
Sir, only adding layer will not increase the efficiency. I think they are changing the sequence also, no?
Okay.
Sir, up to certain layer, it will improve the efficiency, but after means we are using 138 million parameters. Then after adding so many layers, it might reduce the efficiency, and that can cause vanishing gradient effect.
Okay. So basically, you are correct actually. After adding only after adding layers, theoretically, if you theoretically you can prove that accuracy will decrease, but practically it is not happening, and then the reason is vanishing gradient actually. And that's why I was saying that this what you call ResNet, that was the groundbreaking word, because that network has really addressed the vanishing gradient problem. And then now actually you can use same that concept, ResNet concept, and can add multiple layer, hundreds of layer, 150 of layer, different layer, and really you can improve your accuracy. So that's why I call that is a groundbreaking result, because that is one that type of algorithm, or you can say that type of architecture made us work with really deep network. Otherwise, what happen after certain limit, you will find out that your training and the test accuracy both decrease actually. First, people started thinking it is only happening with the training test accuracy, but no, training accuracy also decreases. So basically what does it mean is, you will have good accuracy in training, bad accuracy in test data. Okay. Okay, boss. So this is
Sir, to counter this vanishing gradient, we use LSTM model. So will we cover LSTM?
No, we are not going to cover LSTM actually. So time series version of network, we are not going to have it here.
Okay, sir.
So this is going to be a last concept actually. Since we are going to end this course, I thought to introduce some of this architecture to you people, so that if people talk about this architecture, because if you talk people who know deep learning, they talk about this architecture. So what I thought it is good to know some of popular architecture, and also how to implement this popular architecture through, it may be transfer learning or so. So I'm giving you base to do all those things. Okay. LSTM we are not going to learn here. But that is also what you call, that is also groundbreaking work on deep learning. That I also find that is also good work. Okay.
Sir, which algorithm is used in Google Photos? I mean this architecture.
I think they are using now actually ResNet, or it may be the upgraded version of ResNet. So Google Photo, which
So
one
when
you
we
are?
have more than 2
See, it depend actually. It depend upon application to application. Which one you are asking?
sir, in the Android mobile phone, we will find the Google Photos. So it automatically detect the face.
It may be they are using ResNet, because this belong to Google only.
And once you define that this person is X, after that it will search in all the photos what you have in your mobile and will put all them in one category.
So
Like that.
I don't know exactly. I've not seen that, but definitely they are using this algorithm. I think so. Just check.
Okay, sir.
Because age detection and all, they are using same, the ResNet and all. So I think for that also they are using. Okay, so good. So those who have not completed case study, they just download data, try to finish it, and again I am going to ask same thing. So it is good, and next time I will ask you to show me in a notebook. So it is good you people do it before coming to next class, otherwise don't come to class. Okay, bye boss,
Thanks, sir.
good night.
Good night, sir.